Okay, let's do one more example to see how this motion due to gravity is related to things like centripetal acceleration and circular velocity. So this is problem number 45 from your text, and we have we're going to look at the sun. The sun is orbiting the Milky Way galaxy. So here's our Milky Way galaxy, and it's orbiting at a distance of 3 times 10 to the 4 light years. And a light year is how far light travels in a year, and we'll calculate that in just a second. And we know that it goes around the galaxy once every 3 times 10 to the 8th years. And so the question is, what's the centripetal acceleration that this thing is experiencing? That's the first question. And then the second question is, what is the velocity of the sun in its orbit? Okay, so let's first start with the centripetal acceleration. So I'm going to write down the centripetal acceleration is just v squared over r. And my velocity for a circular orbit, we'll assume it's circular. We're just going to get the total distance it goes. That's 2 pi times the distance divided by the total time, which is the period. And I'm going to go ahead and combine those two things, and I get the acceleration, centripetal acceleration is just 2 pi r squared over t squared divided by r. And I'm going to cancel out one of those factors of r, and I'm going to get 4 pi squared over t squared times r. So that's my centripetal acceleration. And I know what r is, I know what t is, I can figure this out. So let's look at r for a second. So r is in light years, so I get 3 times 10 to the 4 light years. Now that's the amount of distance light travels in a year, so I need to figure out how far light travels in a year. It moves at the speed of light, which is 3 times 10 to the 8th meters per second, and then we need how many seconds are in a year in order to cancel out the time here and just get distance, because we have basically how far light travels in a year. That's a measurement of time in years. And then we have a velocity that has seconds in it. So if you remember, we talked about this before, that the number of seconds in a year is about pi times 10 to the 7 seconds in a year. And this comes from 365 times 24 times 60 times 60. So if you calculate that out, it turns out to be 3.14 times 10 to the 7, which is a cool thing to remember. So I'm going to go ahead and rewrite this. I'm going to get 3 times pi, and then I'll get 10 to the 4 times 10 to the 8th times 10 to the 7. And for our purposes here, this is in meters now, because our years cancel and our meters stick around, our seconds cancel. I'm not worried about super exact numbers here, so a handy rule of thumb is that you can treat pi as 3. So I'm going to say pi is 3 there. So I'm basically going to get 3 times 3 times 3, which is 27. We'll just call that 30. That'll take into account some of the little extra due to pi there. So I get 30 times 10 to the 4 times 10 to the 8th times 10 to the 7 meters. And if I look at that, that's like 3 times 10 to the 20 meters. So that gives me my r. Now my time, I'm going to need that in seconds as well, but I'm going to go ahead and put it in here first. We're going to calculate our centripetal acceleration. I'm going to get 4 times pi squared. I'm going to put in my distance, 3 times 10 to the 20 meters. And then I'm going to put in my time in seconds, which is 3 times 10 to the 8th times pi times 10 to the which is pi times 10 to the 7, and that whole thing is squared. Okay. Now looking at this for a second, I'm going to get 3 squared. We're going to make pi 3 again. I'm going to get 3 squared. In fact, 3 squared is effectively 10. So we're going to just go ahead and say, because we're just dealing with round numbers here, we're going to say that pi squared is effectively 10, so we're going to call that 10. We're going to call 3 squared 10. We'll call pi squared 10. So we're going to get 4 times 3 times 10 divided by 10 times 10. So that's going to get rid of that. It's going to get rid of that. Get rid of that, that, and that. Okay. And in fact, 3 times 4 is 12. That's practically 10. So for round numbers here, we'll just call that 10. So that's all going to cancel out. So all we really care about is the exponents here. So I get 10 to the 20 divided by 10 to the 15 squared, which is 10 to the 30. So that tells me that the order of magnitude of this acceleration is like 10 to the minus 15. Or sorry, 10 to the minus 10 meters per second squared, which is very small. Which is one of the reasons why we can treat our solar system as an inertial frame, because the acceleration that it's experiencing as it goes around the galaxy is vanishingly small compared to all the other accelerations that we experience around the Earth. So now let's look at what the velocity is, because even though that's such a small acceleration, the galaxy is huge, but it's going around like once every 100 million years or 300 million years. So that's a lot of distance to cover. So let's see how fast it's going. So we'll go back to our velocity here. Our velocity is just 2 pi r over t. So I'm going to put in 2, I'm going to put in pi, I'm going to put in my r, which was 3 times 10 to the 20. I'm going to divide that, oops, not by pi, 2 pi r, that's a t. And we're going to divide that by 3 times 10 to the 8th years times pi times 10 to the 7 seconds. So that's all going to be in seconds. So let's go ahead and cancel these out. That's going to go away with that. That's going to go away with that. And we're going to wind up with something like 2 times 10 to the, I've got 20 minus 8 minus, so that's 2 times 10 to the 5 meters per second. And that's something like 700,000 kilometers per hour, which is pretty amazing that something that's experiencing such little acceleration and that's taking so long to go around is going some huge speed. It's quite remarkable what Newton's law of gravity lets us figure out.